so I'm going to talk about validity and availability guarantees of Polkadot shards. So just to get started, we have a single shard here. So there's like the relay chain, and then we call most of these shards parachains, and then we have these other guys, validators and collators, who are going to take part in making this happen. So each shard in Polkadot has its own state and an abstract state transition function. So they all have their own state, but they're sharing state and validation logic with the relay chain. And so we've talked a lot about like heterogeneous versus homogeneous shards, and this actually depends on like what angle you're looking at it from. So like one of the interfaces of Polkadot is that you have to be able to compile your runtime to WebAssembly. And so we have like a WebAssembly interpreter and a compiler within the relay chain client. And so every shard, if you're looking at it from the perspective of the relay chain, it's just presenting a single execute block function that's like an abstract blob of some runtime behind it. But if you're looking from the outside in, then each shard can look different. So you can put in your own modules like balances, democracy, social recovery, or like a smart contracting environment, or just create your own. And so whether or not it's like homogeneous or heterogeneous, it really depends like where you're looking at this shard from. So like from the inside, all the shards look the same. It's just this blob that has like a single execute block function. So actually like getting these blocks to finalization, it starts out with the collators. So parachains have a set of nodes that are called collators, and these aren't really consensus related. So you don't really need to have like any kind of BFT considerations or anything. As long as you have at least one collator, you're basically good to go. And then it's up to you to decide like how you choose these collators. So you could have like proof of stake or proof of authority or proof of work. And so this doesn't really have anything to do with finalization yet. This is really just choosing like who has the right to produce the next block. And so like if you think of it like a pure proof of work chain like Bitcoin, you know, the proof of work is actually like who gets to add the next block to the chain, whereas the finality is like which chain is the longest one. So as far as collators are concerned, they're just proposing blocks for their parachain, but it's up to the relay chain to actually finalize them. So we actually have to like match these collators with validators, and we're going to do that randomly. So we might have like 1,000 validators in Polkadot and say 100 parachains. We're going to actually do this every single block is just based on a VRF. We're going to randomly assign validators to parachains. So if we have like this amount, it would be about 10 validators per parachain. And so then they need to find each other. We actually haven't like finalized how this is going to happen yet, but there's kind of two ways you could do it. One is that all the collators have access to the DHT of the relay chain and can like find these validators, or you kind of make the parachains have like an entry node or like a boot node, so that validators, once they get their parachain assignment, they can just go like start making the connections there. And then once those connections are established, then the collators are going to send a proof of validity to the validators. And so let's go into that, like just a really quick overview. Like you have a state tree, just all the storage entries get hashed, and then they kind of just get concatenated and hashed all the way up to a single state root. And so like this is just a normal like state tree on its own. But we have this thing where like these validators got randomly assigned to one of the shards. But of course, like they can't be full nodes on every single shard. They're basically light clients. So on all of the parachains, they're acting as light clients to the relay chain and full nodes on their own parachain. And then the relay chain is a full node to itself, but it's acting as light clients to all the parachains. So basically, these validators come along to a parachain, and they're a light client, so that they know what like the latest state root is and the last header of this chain is, but they don't have access to the full state tree. So in order to validate this block that they're going to get from the parachain, they need a little bit extra info. So they're going to take like a pruned state tree that only has the modified balances or like the modified storage entries. And so in this example from like the last one, I only changed, I like Louise sent 50 tokens to Ben, so those balances changed, and then a referendum got added to the democracy like storage item. we have this function called onInitialize that basically runs at the beginning of every block. So like in the democracy module, this might check like, are there any proposals that are up for a vote now? And so in this example, there was, and so it got bumped into this referendum count. And so the entries that don't get modified, we can just leave like the hash value, just constant size, and then so we're just passing like a block and this modified state tree. And so this is all the information you need as a light client to be able to validate that this block is valid. So just to like kind of put everything together, because like that's just one parachain, and this is all happening kind of in parallel. So like this is a lot of information here, and we're not going to like be gossiping this all around Polkadot. You're going to have this in every single parachain within this like cluster of 10 validators. So this will be unique for every parachain, and then this just gets gossiped around like a subgroup of 10, and it's not really going to leave there for still a little while. So yeah, just like to back up a little bit, like we could have 1,000 validators with 100 parachains, 10 validators per parachain. Each parachain has submitted a proof of validity, and then they're gossiping that around that group. And then once more than 50% of that group agrees that the state transition is valid, then they start moving on to the next stage, which is to construct a candidate receipt. And so like a proof of validity is really big, and we want something that's constant size. Because like a proof of validity that just modifies like one storage item, that might not be that big, but we really don't want the size of these candidate receipts that are going into the relay chain block to vary based on whatever state transition happened in the parachain. We want them to just be the same no matter what happened, no matter how big that state transition was. So we're going to put together this candidate receipt. I'm not going to like list off every single thing here because you guys can read, but like the main thing here is that everything in this list is constant size. So like the parachain ID and collator ID, this might be like a U32. Signature is constant size. Everything else is like a hash or a Merkle root. And so this stuff just kind of gets like concatenated together into a single candidate receipt. And no matter what happened in this block, this is always going to be the same size. And so the next thing I'm going to go over is the erasure coding part. So yeah, before we move on, like you need to create this Merkle root of the POV's erasure coding. And so we're going to do this. This is kind of how we get away with having only 10 validators per shard. So like ETH2, I think it needs like a minimum of 111 validators per shard, but like 256 to get the finalization within one epoch. And we're kind of here saying like, hey, we can do this with 10 validators per shard without worrying about like collusion or anything. And this is how we do it right here is the erasure coding. So overall, like an erasure coding is a way of taking some message and breaking it up into a bunch of little pieces such that some subset of those pieces can reconstruct the message. And you can kind of choose the subset fraction. So in Polkadot, we set it to 1/3 because this kind of goes along with like BFT assumptions that less than 1/3 of your validator set is Byzantine. And so we're going to create one chunk for each validator in Polkadot, and then you need at least 1/3 of them to reconstruct it, or greater than 1/3. So if we have 1,000 validators, they're each going to get a unique chunk, and then if you get any 334 of these, then you could actually reconstruct this entire POV block. And so we're going to create another Merkle tree with all of the chunks as the leaves, and then compute the Merkle root of that, and then that's what's going to go into the candidate receipt here. And so now we're going to start like actually gossiping this stuff around the network. We're going to send one chunk and the candidate receipts out to all the validators. So you kind of have this like tuple of items that's going to all the validators. The candidate receipt is the same to everyone, and then each validator is getting a unique chunk of this erasure coding with it. And so this stuff starts to like get thrown out all over the network. And at that point, we can start thinking about like how are we going to construct this block of the relay chain, because now we're no longer dealing with like isolated shards anymore. This stuff has started to gossip like all over Polkadot. So your validators are going to be receiving candidate receipts and erasure coding chunks from like all the other shards now. And so they're going to store the candidate receipts in like some other part of memory, the erasure coding chunks, and then the candidate receipts are going to go into the transaction queue. And so when they start thinking about like, okay, I'm going to put together a block for the relay chain, how do they decide like which candidate receipts to put in that block? So first, every like candidate receipt that they're going to put in a new block, it has to have a parent candidate receipt in a previous relay chain block, which of course like you have the state root of the parachain block or the parachain before executing the block, so you can go look this up. And the author has to have a corresponding chunk for that receipt. So it would be possible, since like transaction queue stuff gets gossiped around the network, that and then like the Erasure Coding chunks are actually looking for a specific validator. It is possible that like somebody receives an Erasure Coding or receives their candidate receipts before they've received their Erasure Coding chunk. And so if that validator is selected as the next block author on the relay chain, they're just not going to include that candidate receipt. They're going to wait until they have their corresponding chunk for that. And that's going to go along with the availability guarantees. And then they'll only hold that candidate receipt for a limited amount of time. And then after some number of blocks, if they haven't received their Erasure Coding chunk, they're going to kind of like send out an alert that says, hey, we have an availability problem. I got this candidate receipt, but I never got a chunk for it. And then like that period, we call it the availability grace period. And so if more than 1/3 of the validators say, hey, I got this candidate receipt, but I never got an Erasure Coding chunk, then we're just going to like throw out that candidate receipt and it's done. So these candidate receipts just stick around in the transaction queue for a little while until finally like everybody gets their chunks and they can go into a block. So yeah, now we can start talking about like once this candidate receipt gets into a relay chain block, how are we going to actually get this to finality? So we have to make sure that the validators actually received their candidate receipts, that they actually save them, and that, I should actually say received their Erasure Coding chunks, my bad, that they actually save them, and then that the blocks are valid. So actually save them, this has to do with availability, and then that the blocks are valid, that they're like, valid. So at this point, like we've been in like the validator land for a few minutes here, but now the collators are going to come back. And once they see that one of their candidate receipts is included in a relay chain block, they're going to start asking random validators around the network to give them their Erasure Coding chunks and report any unavailability that they see. And so this is really important. So like this is why we do the Erasure Coding. And so you kind of imagine that like you have a collator who wants to attack a parachain, and he just comes in and submits a new block, and it's a perfectly valid block. But as soon as he submits this proof of validity to the validators, just turns off, goes offline, nowhere to be heard from again. And then this candidate receipt goes and gets finalized by the relay chain. Well, now this parachain is like really shit out of luck because they have a finalized state root, but they don't actually have the pre-image. They don't have like the actual state tree to compute that state root, which means they can never make a valid state transition again. So they're just stuck like forever. And so they need to make sure that they can always get their blocks that are getting finalized back and reconstruct them so that all of their full nodes can stay current. And so they're just going to start asking for their chunks from the validators and reconstruct these blocks. And if they can't, then they're just going to flag this as this block is unavailable and should be thrown out. And then fishermen, which also exist on parachains, they're also nodes that are going to ask for these POV blocks back, but they're actually going to like execute them and report if they're invalid. So you can kind of see that like collators are in a really good position to also be fishermen because they're already asking for this information anyway. But like an important distinction to make, like if you don't want to be a fisherman, collators don't need to have like any kind of Polkadot tokens or anything. They can just deal with their parachain. They just need to be able to send the POV blocks to the relay chain to get validated. Fishermen do need to have some dots because if somebody doesn't have dots, then they could just like throw out arbitrary invalidity reports and spam the chain. So when you submit an invalidity report, you have to kind of stake some dots behind it that says like, yeah, I actually think this is really invalid. And if it does end up getting finalized, then you'd get slashed. So if a collator is okay with owning some dot tokens, then they could also be a fisherman. And of course, like a fisherman wouldn't even have to be like, wouldn't have to have like its own parachain tokens. If you just wanted to like run a full node and own dot tokens, on some parachain, then there's no reason you need to like own those tokens. You could just be a fisherman because you feel like it. So now we get to like the secondary checks that the validators are going to do. And so the collators and fishermen will send alerts that like something is unavailable or invalid, but ultimately it's up to the validators to decide like what's going to the relay chain, and like they're the ones who are ultimately held responsible for it. So besides these like 10 validators that were randomly assigned to a parachain to actually go through the POV process, we're just going to like randomly select other validators again from Polkadot to construct this, like ask for the Erasure Coding chunks, reconstruct the POV block, and validate it. And so only after we've done enough secondary checks can one of these validators actually cast a vote for this block in Grandpa, which is our finalization algorithm. It's a ghost-based thing, so like we're voting on chains and not blocks, and so we can have like a long unfinalized head. And so I think okay, I'll talk about the Grandpa stuff in a second. But so number of secondary checks, like our analysis shows that if you have more than 13 checks, then it would take more than 50 years to get a successful attack by getting like all these validators to like incorrectly attest to something's validity. And so if nobody reports any invalidity or unavailability, it's just going to be like greater than 13 checks that you need. But if some do, then it's going to start triggering like more checks all the way up until you get to like 1/3 of the validator set. So if people start flagging these as unavailable or invalid, then it's just going to start requiring more secondary checks from the validators. And if more than 1/3 of the validators say that this is invalid or unavailable, or that more than 1/3 say it is valid and available, then it's going to be either like rejected or finalized. And of course, if more than 1/3 say both, then we have a problem because that violates our assumptions of BFT that less than 1/3 of the validator set is malicious. So yeah, in Grandpa, like we're voting on chains, not on individual blocks, like one at a time. So it kind of gives like 3 zones to the relay chain. You have like the finalized chain, which is everything that's been like finalized, and then there's a Grandpa voting zone where this is all past the secondary checks, and you can start voting on these blocks now. And then there's a phishing zone where we're still kind of waiting for these checks and reports to get done. And so these, like the phishing and the voting zone are kind of dynamic, right? Like if everything's going smoothly, we predict that like from the time you submit a POV block to the time it gets finalized is about 1 minute. But if people start raising like flags on certain blocks, then these zones can kind of grow or shrink as those reports come in. So some final thoughts, because I still have a few minutes. Like just some of the principles around this is, in order to scale the system, we want to push as much information to the edges as possible. And like we don't want the relay chain to be any kind of bottleneck. So number one, that lets us do like the having the different zones in the chain, is that block production is not on the critical path for finality. So like other PBFT-based algorithms, they'll like do the block construction and finalization all as part of the same round. But since we separate those into 2 things, we can kind of have this dynamic chain that has different zones in it, and finalize like only when we think it's appropriate without actually slowing down the rest of the chain construction. Relay chain information is always constant size, so we're basically only putting like IDs and Merkle roots and state roots, stuff like that in there. Collators and fishermen increase with the number of parachains, so like you have to do all these like availability and validity checks. But as you add more parachains, the collators and fishermen exist on the parachains, not on the relay chain. So this stuff all scales with the number of parachains, and it's not really adding parachains in this sense doesn't add any extra load onto the relay chain. They're taking responsibility for that themselves. And then cross-chain message passing, which didn't really talk about here, except that like the Merkle root of outgoing messages will go into this candidate receipt. But the way that works is that if 2 parachains share any full nodes, like even if they're not validators or collators, since this message root is going to the relay chain, they can just pass this message via their shared full nodes. Doesn't even touch the validators at all. And then if they don't share any full nodes, then yeah, the validators will kind of do like a push and pull model to get these messages where they need to go. But the messages are still never going into the relay chain itself. They're just being gossiped by the validators. And then finally, a Hermit relay chain, which is pretty cool. So we talked about like parachains only here, but of course we do have actual transactions as part of Polkadot, like transfers, governance, staking, all this stuff. We actually want to move like all of that outside of the relay chain. So there would be like a parachain for dot balances, a parachain for staking, a parachain for governance. And so in that case, the relay chain would literally just have candidate receipts of parachain blocks, and it wouldn't have any kind of these like Polkadot transactions. And so like Polkadot would be a parachain of Polkadot, which is pretty cool. So yeah, I think that's it. So I think I have a couple minutes for questions, or we started late, so the next person can go. Yeah.
What are the best resources online that kind of go into this?
Yeah. So I actually just like wrote. So there's like the Polkadot wiki, which we've been putting quite a bit of work into. And then I actually like based. Oh shit! I don't have internet. I based this talk off of a blog post that I just wrote. I can hotspot my phone real quick and throw it up here. See how long. Yeah. Oh, here we go. Come on. Yeah, so like everything I just talked about is part of this thing that I wrote on our blog. So I guess that resolution is not very good, but it's polkadot.network. So I kind of did all this here, so you can check that out. Yeah? So yeah, the question is like, how do you decide which nodes keep track of which chunks? It's just like every single validator is going to have a chunk from every parachain. So then they just get kind of random, like every validator has a validator ID in storage. So you can just like take your chunks from like 0 to 999 and then just like queue them up with the validator IDs from 0 to 999. Yeah. All right. Any more? Cool. Thank you guys.